Welcome to the first module of the massive online open course, Geoscience, the Earth and its Resources. This is the first step of a long journey which will provide you a more profound understanding of how the Earth works. Eventually, this will enable you to predict the nature of the subsurface of the Earth. You will also learn to use the Earth's resources in an efficient and responsible manner. The journey of this MOOC is organized in 5 main steps. A general acquaintance of the Earth, horizontal and vertical movements which lead to the formation of mountains and sedimentary basins, how sediments are produced and then transported to the sea, and how different types of sediments are deposited in the marine environment. The last 2 components of the MOOC are dedicated to 2 of the most important commodities relevant to geological studies: hydrocarbon and water. The Delphi engineers want to understand, but also to use their knowledge. Like most journeys, your time and energy are limited, so we will focus on subjects of primary importance. This course is only the beginning of your geological life, and you will have plenty of opportunities to deepen your knowledge in the future, in Delft or elsewhere. Here you see the rock cycle. You see clouds and rain erode the mountains, producing sediments, which are then transported to the sea. At subduction zones, sediments and other rocks are brought at depths of tens of kilometers and metamorphosed. Some might even melt, forming magma and magmatic rocks. Others come back to the surface. 3 types of rocks are defined: magmatic, metamorphic, and sedimentary rocks. We will start our journey with magmatic rocks, which form from the consolidation of magma at depth or at the surface of the Earth. These 2 types of rocks are very different and are named intrusives and extrusive. You will see more of this in the coming slides. Where does the magma come from? The answer to this question is not obvious, as practically all rocks of the outer 3,000 kilometers of the Earth are solid. Where does then the magma come from? How is this generated? We will need a bit of physics and chemistry for this part of the journey. In this diagram you see 2 curves. The geothermal gradient indicates temperatures found at different depths in the Earth. The dashed curve shows the temperatures at which typical mantle rocks melt. As you can see, temperatures are lower than melting temperatures, which means the rocks are solid and no magma is generated. Now, how can we bring then a rock to melt? The first process is simply heating. We call this creating a thermal anomaly. This is feasible, but physically very difficult in the deep Earth. A second possibility is to move the rocks upward. This is potentially a good mechanism, but movements of many kilometers are needed. The third process relates to the change of position of the melting curve. When fluids are added to the system, the melting curve shifts to the left and rocks previously in the stable field starts melting. This is what happens in subduction zones, where fluids are added to the crust, thereby lowering the melting temperature. During progressive melting, a very important process takes place, which is called fractionation. As a result, the magma generated by a rock can be chemically very different from the parent rock. This is caused by the fact that the rock is typically composed of different minerals with different melting temperatures. With increasing temperatures, the first minerals to melt are those with a low melting temperature. The resulting magmas will have a percentage of silica SiO2 much higher than the original rock. With increasing temperature, a larger portion of the rock will melt and the composition of the magma will approach that of the parent rock. As a result of fractionation, limited melting produces magmas which are acid and relatively cold, 600–700 degrees. Magmas generated by complete melting, on the contrary, are more basic and have generally higher temperatures. The magma has a density lower than that of the surrounding rock and will start moving upward, driven by the negative density difference. We call this buoyancy. A simplistic but interesting quantity description is provided by Stokes' law. This shows that the velocity of the rising magma bubble is directly proportional to the density difference and inversely proportional to the viscosity. Driven by its lower density, the magma will begin moving upward. Magmas, which are relatively cold, have a high viscosity, will move slowly and are likely to remain trapped somewhere in their path towards the surface. They will consolidate and an intrusive rock is formed. Intrusive rocks are typically coarse-grained, and you can see in thin section that the entire rock is built of fully developed crystals. Intrusive rocks are of great importance. They provide the heat driving most geothermal fields and emit fluids which generate major ore deposits worldwide. Hot magmas have low densities and very low viscosities and are likely to reach the surface of the Earth, creating volcanoes, one of the most fascinating phenomena in nature. Volcanoes show very different characteristics and behavior depending on the magma. High temperature magmas produce large but flat edifices. The lava flows gently and regularly out of the crater. Low temperature magmas, on the contrary, form steep and more irregular complexes and are much more dangerous, with frequent explosive activity. In this last slide, you find a scheme for the classification of magmatic rocks. In a plot showing the percentage of silica SiO2 versus various types of minerals, you can see that different domains correspond to different types of rocks. And as you can see, two different names exist for each composition, one for intrusive and one for extrusive rocks. We have now looked at magmatic rocks, and now you are ready to tackle the second type of rocks, namely metamorphic rocks.